Merry Christmas.
Check out that shirt. Show him. Show
You
him.
want to see it?
You want to see it? I want to see it.
All right.
Leave it on.
Yo, mister, that's lit.
Yeah.
Literally.
We're here with lecture 4, heat flow and heating and cooling curves for our physical behavior mapping.
Ooh,
What are we focusing
We got to be
on
able to
here
draw
today?
these and label them. So let's do it up. Let's get right into it, right?
We're going to track changes in heat.
Yeah. See these curves on the pictures? We got to be able to draw them and label them
Mhm.
and understand them.
For sure.
Right.
But what a basic heating and cooling curve is, it's a plot, it's a graph. It shows how temperature is changing when heat is being absorbed or released into a system, like a beaker containing water.
Right.
Okay.
The key is to constantly, just because temperature doesn't change, doesn't mean we're not still adding the heat.
Right.
We are still constantly adding the heat at a constant rate. So that's a key piece.
So let's get to what kinetic energy is and how it relates on this graph.
Okay.
It's the changing when temperature is changing. Because kinetic energy is the energy of motion of atoms. Atoms cause things to, the faster they move, the hotter they feel to us humans. Right. So that's how we're saying kinetic energy is changing when temperature is changing.
Right.
This only occurs in certain portions of these graphs. We call them the slants.
Sure. Now let's show you what those slants look like. Mm-hmm. That's where they're literally slants.
It's got a slope. The slope is not zero.
And if you follow the slope and your y-axis, you're moving along the y-axis as you're on those slopes.
Right.
So I got a different temperature.
And the y-axis being temperature tells you temperature is changing. Right. So now potential energy is the opposite of kinetic energy. When kinetic energy is changing, potential energy is not.
And when kinetic energy stops changing, but I'm adding heat, potential energy must be changing.
Because potential energy is the energy of position. It's the energy, the heat that we're adding in these portions where the phase is changing. It's going into changing the phase of matter from a solid to a liquid.
Like literally the position of molecules related to each other.
And they can't move any faster when they're trying to move apart.
Right. So this is where the
Flats
are. And notice in the picture there, it says gas to liquid, and both phases are present, and that's key. Multiple phases are present during phase changes. Because we'll get into the equilibrium about that later.
If you look at the x-axis, it's time. And it takes time to condense something. It takes time to melt something. It takes time to freeze something.
Right.
So that is important to know, that both phases will be present in the flats.
Right. So let's draw our own.
Yeah.
You guys got a little bit of space.
Yep.
Before we get too far into this, you might want to watch this more than once because there's going to be a lot of labeling going on.
Mm-hmm.
You might want to watch it and then bring it back and then watch it again.
Right, small.
Yeah.
Right.
There's going to be a lot to write on this little graph.
Overlap things. So
first the axes, right? Always first the axes.
Temperature is going to be on the y-axis because it's changing. Yep. And time's usually always on the axis.
Yeah, and very rarely is it not.
Yeah. So.
And then it's a heating curve, so we better start low and go high. And what are we drawing?
3 slants and 2 flats.
3 slants and 2 flats.
In this order, it has to look like this if you're asked to draw a complete heating and cooling heating curve.
Yes, and it does. Yeah, because if I were to have any of them connected slant, flat, you wouldn't see a difference in the slants.
Right.
So the only way to do it is literally this way.
So let's label it up with the phases and the phase transitions and the melting and boiling.
Since we started low, we'll start low.
So the coldest phase would be solid.
There you go.
And
then we go into the first phase change, which in a heating curve is melting, where I go from solid to liquid. So those 2 phases are in equilibrium, solid and liquid. They're going back and forth. We'll get into that a little bit better later.
The super important thing about here is when you graph data and you track the flats over to the y-axis, you can actually find the melting or the boiling point.
Right. Or backwards, if I know that this is water and this is the melting point, I know water melts at 0, and I can go ahead and label this part 0.
Right. Okay. Then after we've completely melted, we
must be
totally liquid.
1 phase.
Mm-hmm. And then once we heat this liquid up to the point where it starts to boil,
making noodles, some of the molecules are going to be in the liquid phase, some in the gas phase, and then I can actually track over now to what my boiling point of my liquid is. If the liquid is water,
it's got to be 100 degrees.
This would be 100 degrees of the
If it's a
point.
different substance, it would be a different temperature, but it would still be a flat spot.
Yes, that's key. The flat would still be
Be
there.
a flat spot.
The number of which it boils would be different. That's all. Right?
And then once it's completely boiled, it's a gas, and you can heat the gas up to the pretty much any temperature. I mean, thousands of degrees potentially. That's why there's no more flats, because there's no other phases of matter to go into.
Now, so if the temperature is changing on the slants, if the temperature is changing, and temperature is a measure of heat, which is kinetic energy, kinetic energy is changing. But that's kind of logic, right?
For sure, yeah. So temperature equals kinetic energy is what we need you to burn into your brain.
Yeah. Temperature change is a change in kinetic energy, because kinetic energy is really heat,
Now,
temperature measures
you
heat.
can't have two types of energy changing at the same time. So once you've got everything once you hit that melting and the boiling point, the potential energy, the position of molecules is actually changing.
Yeah.
The potential energy changes, but the temperature doesn't.
Right, you're going to get that spot there in the phase change where I'm still adding heat, but the temperature doesn't change. That does happen because what's happening is that energy that we're still adding is going into rearranging the molecules into the next phase.
Yeah. So let's see what else we got here.
Yeah, so we just got to fill in these pieces.
Fill in these parts. So the important points on the graph, melting point and boiling point. So those are the flats. Lower flat's got to be your melt. Higher flat's got to be your boil.
And then there's the phases. So the lowest slant is always solid, the middle slant is liquid, the highest slant is gas. It's actually the same for both curves.
Where are we seeing two phases mixed?
During the
Flat
phase change.
portions, the flat
The
portions.
phase changes.
And where is kinetic energy changing?
All slants.
Every time. And potential energy changes only in the flat.
Nice. So now we're going to go on to a cooling curve, which is very much the same. So we'll actually pick up the pace a little bit.
So
Sound good?
there we go. We got to
Draw
label
our
it up.
axis.
Temperature on the Y, time on the X. Draw your slants and flats. 1, 2,
Right.
3.
But now it's a cooling curve, so we'll start
High
high.
and go low.
There you go.
Let's label up our phases, our melting, boilings, and
Yep,
transitions.
So we got gas first,
Then
right.
vaporization. I'm sorry,
Condensation,
condensation, which is
because
the opposite of vaporization.
which is the same point. This would be the same temperature if it was water. I'm just cooling now, so we just give it a different name, a different phase change.
Heat's flowing in a different direction here.
Right.
Then we get to a liquid once everything is condensed.
Yep, only one phase.
Mhm.
And then after liquid, now we're going to actually freeze.
Yep.
And we could also call this point fusion,
Yes, very
right?
much.
Melting or freezing, this flat. And again, we can chart over to the
Find the
y-axis.
actual value of the
Find,
freezing
right.
point.
And then after we freeze, we all know that we're going to become solid.
For
We're
sure.
good with that.
Yeah.
And then guess what? All the flats are,
Potential energy, and all the slants are kinetic.
there you go. So there's a slant. Sorry, I said the wrong thing. So slants are kinetic energy changing,
And
Just like the other.
flats are potential.
just like the other chart. There you go.
There we are. Next.
Yeah, boy.
Same setup. Where are we going to find the condensation and the freezing point, or the fusion point of fusion?
There you go.
Flats. Higher flat is the condensation, lower flat's the freezing.
Right. We got to know that those are what we call phase changes.
Yeah. Solid only, liquid only, gas only, the slants. High,
The
middle, low.
slants. This time they're written in a different order, but notice it's still gas is highest, liquid is middle, solid is lowest. We just started with gas, so I wrote it first.
Sure. Solid, liquid, and liquid and gas. So this is our flats when our phase transition is occurring. You have both phases present. What it's
Right.
coming from and what it's going to are both in there at the same time.
Right. And when the kinetic energy is changing, that's always going to be at a slant. When the potential energy is changing, that's always going to be at a
Flat.
because now the kinetic energy isn't changing.
So let's really quickly hit up endothermic, exothermic, heat absorption, and release
Okay.
as related to these
Well,
phase
because
changes.
exo makes sense, let's start there.
Okay. So exothermic means that heat is being released from the system.
It's literally exiting the system, and
And
it
the
sounds
system-
like exothermic.
And the system is the beaker, so it can leave to the room, and that's okay.
Right. So then if we can figure out exo, then endo's the opposite.
Heat is entering the system.
And if you
So
look at it
coming
from
into
this,
the beaker,
from the beaker and the water's point of view, it's absorbing.
the heat.
We would be adding the heat, but
Beaker
the system itself
absorbs
absorbs it. So it's just a point of reference.
So let's get our definitions here. So
Alright,
this
so-
is where heat is being released. So from a vapor to a water to ice.
Right. Cooling. So that's exothermic because when I cool something, heat must be exiting that system.
Right. That beaker itself is getting colder, so the heat must leave it.
Correct.
So
And the opposite is, of
endo,
course,
which
is
means
heating.
go from ice to water to gas.
Absorbing heat, getting hot, getting
So that
warmer.
beaker, I'm adding heat to it. It's absorbing the heat that I'm adding to it. So and heat is entering the system, which is the beaker, and it's getting hotter. It's going through its phase transitions, and that is it.
Eventually it's boiling.
We're going to skip the whole deposition and sublimation.
Yeah, we'll
part.
get there later when we label up all the phase changes.
There are 4 pages of practice here for you to do.
Yeah.
And that's really all there
Yeah,
is
you
to
basically
it.
gonna have to draw some of those on your own just from scratch. The axes will be there. You'll have to label it up.
Memorize, memorize, memorize.
Yeah, it's that simple.
Thanks for watching.
See you guys.